We begin today with the same guiding question as yesterday. And we're going to learn today actually what this Taylor and Maclaurin polynomial are. We did just a taste of that yesterday. Yesterday, if you recall, we reviewed how a tangent line can be used to approximate the value of a function. And we looked at how we could expand that into a quadratic. And what we're going to do is look at a different function today, but with the same intent. We're going to approximate a value and we're going to expand our understanding of that approximation. So we begin here with our friend, our long-term friend, our friend that has been around for a very long time, our buddy, the tangent line approximation. Hello, friend. We refreshed our knowledge of this yesterday, so I'm just going to jump right in. We know that to write the equation of a tangent line, we need the slope, which means we need the first derivative. First derivative of e to the x is e to the x. We need the first derivative at a value close to the value we're approximating. I think you'd agree that 0 is awfully close to 0.1, so that's acceptable. So the slope at 0 is 1, and we need the coordinates of the point that the tangent line goes through. And that point is shared by the tangent line and the function. That means f of x is approximately equal to p sub 1 of x. Please recall this notation from yesterday. That means the first degree polynomial. And that equals f of 0 plus f prime of 0 times the quantity of x minus 0, or f of 0 is 1, f prime of 0 is also 1, and this is no different from what it has always been. That has been for a very long time, and actually for always and forever in the future. I guess unless we completely reinvent math. I don't think that'll happen. The equation of a tangent line. So we're going to use that equation of a tangent line to approximate, just like we always have, a value of x. So if we choose the value of x that's 0.1, we get an approximation of 1.1. Which we can determine our error by subtracting the value of e to the power of 0.1 and 1.1. I use the absolute value there so that the order doesn't matter. So here's my calculator. Should show up okay, I think. All right, so I want e to the 0.1 power. So that's that. Subtract off 1.1. That's our error. That's how much we're off by. That's really accurate. Really accurate. Like we're within 2 decimal places already. And all we did was use a tangent line, which was really easy to come up with and really easy to execute without a calculator. And remember, that's where this tradition comes from. It comes from the time before calculators. And incidentally, it is still with us because this tradition is how your calculator literally gets e to the power of 0.1. It uses an approximation scheme. It may not use the polynomials that we're looking at today, but it uses something similar. Okay, so tangent line. This was the new stuff. The tangent parabola, the second degree polynomial. It's the same f, the same value, and that means everything else is the same. We have f prime of 0, f of 0, and p sub 1 of x. None of that has changed. What we're going to do is use this to help us write a tangent parabola. And as we talked about yesterday, the the tangent parabola looks like this. So we have our tangent line from the first part, which is still f of 0 plus f prime of 0, times the quantity of x minus 0, which is 1 plus 1 times quantity of x minus 0. We still have that. We add on the squared term. That's what turns this into a parabola, this squared term right here. So we have f of 0 plus f prime of 0 times the quantity of x minus 0 plus f double prime of 0 divided by 2 times the quantity of x minus 0 squared. That is the equation of our tangent parabola. Well, not the equation, but that's how we get the equation. All right, well, that's no problem because e to the x is one of the coolest functions out there. It's its own derivative and antiderivative, e to the x. You are something special. I don't say that to all the functions e to the x, just you. So f double prime of x is e to the x, f double prime of 0 is 1. We can write this. So f of x is approximately equal to p sub 2 of x, which is f of 0 plus f prime of 0 times quantity of x minus 1. That's the tangent line, right? Tangent line part. Plus the new part, the quadratic part, f double prime of 0 divided by 2 times the quantity of x minus 0, which, if we use 1 for f double prime of 0, gives us a 1/2, just like it says, 1/2 times quantity of x minus 0 squared. When we approximate 0.1 this time, we get 1.105. So we have the tangent line approximation, right? Remember this, the 1.1, which we got from before. And we're adding on one half times 0.1 squared, which is where we get the 1.105 from. So we take the tangent line value of 1.1, we add on that value right there. Oh, that's done a little bit too far. Sorry about that. Now you can see what I mean. Okay. Error calculation then is the same thing. It's the difference between the true value, which our calculator calculates for us, and the 1.105 we came up with. And it's 0.00017098181, which I think you would agree is smaller than 0.005 and incredibly accurate. We are within already 3 decimal places of accuracy. And all we've done is used a tangent parabola, which, by the way, was not all that hard. We had to take a derivative, and then we got 1 plus 1 times 0.1 plus 1/2 times 0.1 times itself. We could do all of that without a calculator. Pretty sweet. But not accurate enough, right? This is math class. This is not science class. This is not English class where precision doesn't matter. This is math class. Precision matters here. So how do we get more precision? And you already know the answer to this because you've been studying calculus for a while. Well, if one thing was good, 2 is gooder, 3 is gooder than that. So let's get 3. Let's go for a tangent cubic, a third degree. And we're doing the same stuff. So same function. So same function, e to the x, same value, 0.1, same x value for approximation, 0, same first derivative, second derivative, by the way, same third derivative. It's a shame that doesn't happen. It only happens with this function. Thanks, e to the x. You're one of the good ones. So P sub 3, which is approximately equal to f of x, is the tangent line in green, f of 0 plus f prime of 0 times the quantity of x minus 0, plus we add on the quadratic part, which is what got us the 0.005, remember? So we have 1.1 plus 0.005. We need the cubic. And we know that the structure of the cubic is like the structure of all the others. Namely, we have some value multiplying x minus 0 cubed. The problem is we need that value. We need that value. So we've already got 1.105 from our previous approximations. We need that value. How are we going to get that value? Well, in order to get that value, we're going to do the same reasoning we did yesterday to get the f double prime of x divided by 2. Namely, f prime and p sub 3 prime, those need to be the same. F double prime and p sub 3 double prime. And finally, f triple prime and p sub 3 triple prime all have to be the same. Those have to be true statements. If they're not true statements, we got no tangent. Okay, so let's look at what p sub 3 prime is. P sub 3 prime means I'm going to take a look at this statement here and literally take the derivative of each term. So f of 0 is a constant. Derivative of a constant is 0. We do f prime of 0 times the derivative of x minus 0. The derivative of x minus 0 is 1 plus f double prime of 0 divided by 2. We multiply that by the derivative of x minus 0 to the second power, which is 2 times x minus 0, that quantity, times the derivative of x minus 0, according to the chain rule, that's 1, plus a sub 3 times the derivative of x minus 0 cubed, which is 3 times the quantity of x minus 0 squared, and then chain rule says take the derivative of x minus 0, which is 1. You don't actually need the chain rule here because it doesn't change anything, but it's been a while since I got to say chain rule, and I missed it. So I'm going to say chain rule a lot today to remind you that the chain rule is always present when you take a derivative. Okay, so f prime and p sub 3 prime, those are the same. Let's look at p sub 3 double prime. P sub 3 double prime means I'm going to take f prime and I'm going to find its derivative. The derivative of 0 is 0. The derivative of f prime times 1 is the same thing as the derivative of f prime. F prime is a constant, so that's 0. F double prime divided by 2 times 2 is f double prime of 0. The derivative of x minus 0 is 1. The derivative of a sub 3 times the quantity of x minus 0 squared is 3 times 2 times the quantity of x minus 0 to the first power. Chain rule, multiply by 1. So that is our second derivative. How are we get a third derivative out of this? We take the derivative of the second derivative. Looks like that. The derivative of 0 is again 0. The derivative of 0 is again 0. The derivative of f double prime of 0 times 1 is the derivative of f double prime of 0. Since f double prime of 0 is a constant, it is 0. So we have a sub 3 times 2 times the derivative of x minus 0, which is 1. So we can simplify and say f triple prime of x, the third derivative of f of x, is a sub 3 times 2 times 1. Or, as we're interested in knowing what a sub 3 is, a sub 3 is f triple prime of x divided by 3 times 2 times 1. So that means we can finally go back to our formula from all the way up here and replace a sub 3 with something we can actually work with. F triple prime of 0 divided by 3 times 2 times 1. So our cubic polynomial, our third degree tangent, that's approximately f of x, is f of 0 plus f prime of 0 times the quantity of x minus 0 plus f double prime of 0 divided by 2 times the quantity of x minus 0 plus f triple prime of 0 divided by 3 times 2 times 1 times the quantity of x minus 0 cubed, which, substituting in the values, we have f of 0, f prime of 0 times x minus 0, that's the tangent line again, plus 1/2 times the quantity of x minus 0 squared. That was the part we added when we changed it to a quadratic, plus our new part, 1 divided by 6, 3 times 2 times 1 is 6, last time I checked. F triple prime of 0 is 1 because it's again e to the power of 0. And our approximation using p sub 3, and I got that on my calculator. I won't make you watch me type it in, but you too can get that on your calculator. 1.10516 repeating. So our area between the true value and our approximated value is all the way down to 0.0000425. That is mega tiny, super tiny. That's really good error, isn't it? Think about the last time you were in science and you did one of those experiments and you had an error that small. Probably never. Now, of course, for math, that is not precise enough. We need more precision, but more on that in just a bit. So real quick, I just want to remind you that we've added 0.00016 repeating, and 0.00016 repeating is what we get if we do 1/6 times 0.1 to the third power. So each time we add a term, we add a little bit more accuracy. That's kind of the idea we're going off of. So if we wanted more accuracy, we would add a fourth degree term, more accuracy, a fifth degree term, more accuracy, a sixth, and a seventh, and an eighth, and your calculus tells you how many terms you want. All of the terms, infinitely many terms, would result in perfect accuracy. Zero error, perfect accuracy. Okay. So this process, this formula, this technique is named after this person, who is the person that wrote it down in the person's paper that we studied. So not to say that this is the first person to ever come up with this, but it is to say that this is the person that we named it after because it was this person's math paper. So we have f of c plus f prime of c times x minus c, that's the tangent line, plus f double prime of c times quantity of x minus c squared, that's the quadratic, plus f triple prime of c times quantity of x minus c cubed. And we go all the way to the fn of c times quantity of x minus c to the power of n, but we have something that we're missing. Did you notice that we had these factorials present? You might have noticed this one, right? Because I kept writing it as 3 times 2 times 1, and you know that 3 times 2 times 1 is a factorial. I didn't write this one as a factorial because 2 is 2 times 1, so 2, but it is a factorial. Similarly, we could have for the first degree term a 1 factorial, which is 1, which is why you don't see it in the formula, and a 0 factorial for the 0 degree term, because that is also 1. So our Taylor polynomial creates terms by doing fn of c divided by n factorial times x minus c, that quantity, to the nth power. This notation, forgive the pen change, I had pens that died on me in the middle of writing, means the nth derivative of f of x. The nth derivative of f of x. We haven't used that notation for a very long time. Last time we saw that was way back when we first learned about repeated differentiation. So here it is again, me reminding you, I know it's been a while. Okay? And there's this c on there. We have no idea what the c is. What is the c? The c is the center or location. So do you remember how the tangent line was located at 0? The center was 0 for that example we just did. So c is whatever value you are locating your tangent line, parabola, cubic, whatever, Taylor polynomial. Now this Taylor polynomial, when c is 0, has a very special name. It's called a Maclaurin polynomial. And again, this is named after the person whose math paper was published and looked at. Not to say this was the first person who came up with it, but this was the person whose paper we have in our historical record of math. So those are the two big takeaways. And there's a third and final big takeaway I want to mention, which is the error. So you recall yesterday I talked about the error, how we could specify the error before we begin our calculation. This is what I'm talking about, this kind of idea. So if you go back to the problem we were looking at, we added on each time a little bit more. So we went from 1.1 to 1.105 when we added the squared term, to 1.10516 repeating when we added the cubic term. The error, what we're off by, this value right here, 0.0000425, I think I said enough zeros. That's all of the terms we didn't calculate, all those terms that were unused. So if we were to add up the fourth term through the infinite term, that would represent the approximation part we are missing. We will spend more time talking about the error in the future. But for right now, if you have these three big takeaways, the Taylor polynomial formula, the understanding that the Maclaurin polynomial is a Taylor polynomial when c equals 0, and the error actually represents the terms we didn't calculate, the unused terms, as I called them here, then you are in excellent position for understanding where we're at.